Section 1.4 talks about complex numbers and quadratic equations in the complex number system. In the last chapter, I said that quadratics can have complex roots, and those complex roots would be conjugates, and we should talk about what that means. So first things first, complex numbers. So the imaginary unit I is defined as the square root of -1. And this is imaginary because there's no way that I could take a negative times a negative and get a negative, or a positive times a positive and get a negative. We can't take the square roots of negative numbers. So these numbers are called imaginary. Because I equals the square root of -1, I squared is -1. It's also important to note that this notation was first used by Rene Descartes. He's the one who came up with the Cartesian plane and just was an all-around cool math guy. So we call I the principal square root of -1. So for any real number, b, the square root of -b equals 1 square root of -b. So why don't we go ahead and solve a few examples. If I have the square root of -100, the first thing I'm going to do is I'm going to pull out that I. I don't want it there. So that's going to give me I square root of 100. Well, the square root of 100 is 10. Now, I is a radical, and remember we write radicals after our whole numbers, so we're going to have 10I. For this next one, I have the negative square root of -36. So I've got -I square root of 36. Well, the square root of 36 is 6. So this is going to give me -6I. The square root of -2 is going to be I square root of 2. And the square root of 54 is going to be I square root of 54. But then I have to simplify 54. 54 is 2 times 27, which is 9 times 3, which is 3 times 3. So I've got a perfect square I can pull out of there. And we're left with 3I square root of 6. And if you didn't understand how I simplified the square root of 54, please go review our chapter or videos. So as long as a and b are real numbers, then any number of the form a plus bi is a complex number. Now our complex numbers have both real parts and imaginary parts. A would be the real part, and b would be the imaginary part because we're multiplying b by the square root of -1. When we're adding and subtracting complex numbers, we add the real parts and we add the imaginary parts. So 2 plus 3i plus 6 plus 4i becomes 2 plus 6, which is 8, plus 3i plus 7, 3i plus 4i, which is 7i. I can even do this for multiple numbers. I'm just adding multiple, I'm just adding more than 2 parts. So I've got 4 plus 3, that's 7, minus 6 is 1. And 2i minus I, that's 1i, plus 3i is 4i. Remember to distribute the negative when subtracting. So I've got 6 plus 5i minus 3 minus 2i. That gives me 3 plus 3i. I have 7 minus 3i minus 8 plus 6i. 2 negatives make a positive. That gives me -1 plus 3i. So here's how we would add and subtract complex numbers. Don't forget to distribute that negative. When we're multiplying complex numbers, it's important to remember that I squared equals -1. So we can simplify. If I have 4i times 2 plus 3i, that's going to be 8i plus 12i squared. Well, I squared is -1. So I've got 8i plus 12 times -1. That's just going to give me -12 plus 8i. When I've got a complex number times a complex number, we're going to multiply this like binomials. We're going to FOIL. That's going to give me 12 minus 6i plus 20i minus 10i squared. So I'd have 12 plus 14i. -10 times -1 would be +10. Final answer is 22 plus 14i. This next example, we'll do number 3. I'm going to switch colors. 3. 2 times 1 is 2. 2 times negative 5 is a negative 10i, plus 3i minus 15i squared. That gives me 2 minus 7i plus 15. So I've got final answer 17. Let's make that look like a 17. 17 minus 7i. So we're always just going to make sure we only have one I left. We want to combine like terms. When we're dividing complex numbers, what we need to remember first is that we do not like having radicals in our denominator. And the square root of negative 1, I, is a radical. So we're going to have to multiply by the conjugate. So let's go ahead and divide these. So for number 4 right here, I've got 8 plus 9i over 5 plus 2i. And in order to eliminate what's in the denominator, I'm going to multiply by the complex conjugate, which is 5 minus 2i. This will cause my denominator to be a real number. So on my denominator, I'm going to have 25, because we FOIL, minus 10i plus 10i minus 4i squared. That gives me 25 plus 4, so I'm going to have 29 in my denominator. For my numerator, I'm going to have 8 times 5, which is 40, minus 16i plus 45i minus 18i. That gives squared. That's going to give me 40 plus 18, which is 58, plus 45i minus 16i, 29i. Well, now we can already simplify. 58 divided by 29 is 2. 29i divided by 29 is I. Last but not least, let's change colors and work through number 5. I've got 1 plus I. I'm going to multiply both by, not the square root of I, my bad, just by I. This will give me, in the I times I, which is I squared, which is negative 1 in my denominator. And then I'll have I plus I squared, so that's just I minus 1. And then I go ahead and divide by a negative 1. That gives me negative I plus 1. And I need to rewrite this so I is second, so I have 1 minus I. So here's some examples of complex conjugates. It's denoted with a bar over it. That just means we switch our middle. If I'm adding, I switch to subtraction. If I'm subtracting, I switch to addition. If I just have I, then it's just I. So we've already rationalized a couple denominators, but let's go ahead and do it again. I'm going to multiply this by 3 minus 4i. 3 minus 4i. 3 minus 4i becomes my numerator. My denominator becomes 12. Nope. I'm thinking one step ahead. 9 minus 12i plus 12i minus 16i squared. That means my denominator is going to be 9 plus 16, which is 25. So I have 3 minus 4i over 25. For our second one, we're going to multiply by 4 plus 3i. I'm going to do my numerator first. That gives me 8 plus 6i minus 12i minus 9i squared over 16 plus 12i minus 12i minus 9i squared. 8 plus 9 is going to give me 17. 6i minus 12i is a negative 6i over 16 plus 9 again. I'm so creative, y'all. 16 plus 9, which is 25, and I can't simplify this any further. When we're working alone with I, it's important to remember I squared is negative 1. So I cubed is negative I, and I to the fourth is 1. So if I can rewrite these as products of any I to a specific power, it's going to continue to follow the same pattern. So if I have I to the 12th, that's I to the fourth cubed. Well, I to the fourth is 1, and 1 cubed is just going to be 1. If I have I to the 39th, that's I to the let's think of some good ones. 36 is divisible by 39 divided by 4 gives me 9. 36. Okay, so this could be I to the 6. We can pull that apart. Times I to the third. I to the 36 is I to the 4 to the 9th, right? Well, that's going to be 1 to the 9th times I cubed, which is just 1 times I cubed, which is just negative I. I to the negative 2 and I to the negative 1. Friendly reminder that those are just going to be fractions, right? We put those in the denominator. So if I have, let me go ahead and clear us some space, change colors. I squared, that's going to be I to the negative 2. That's 1 over I squared. Well, I squared is just negative 1, so I'd get negative 1. If I have I to the negative 1, that's going to be 1 over I. Well, that's still a radical, so I have to rationalize my denominator. I would just get I over I squared, which is I over negative 1, so that becomes negative I. So let's go ahead and solve some quadratic complex solutions and write them properly. For this first one, I'm going to use the square root property. I've got x equals I squared root of 9. Sorry, plus or minus. Plus or minus I squared root of 9. So x equals plus or minus 3i. There we go. If I have 3x cubed plus 4x plus 5, I'm going to use the quadratic formula to solve. X equals negative b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. So x is negative 4 plus or minus the square root of 16 minus 60 over 6. X is negative 4 plus or minus the square root of negative 44 over 6. I can simplify 44 into 4 times 11, which is 2 times 2. So I can pull out a power of 2 and an I. So I've got x equals negative 4 plus or minus 2i square root of 11 over 6. And then I can go ahead and pull out a power of 2, a factor of 2. So I've got negative 2 plus or minus I square root of 11 all over 3. And those are going to be our two complex solutions, and they are conjugates of each other. Friendly reminder about discriminants when we're working with quadratic equations. If they're negative, then our solutions are going to be complex.